I forgot. So it doesn't matter. So let me get started with and finish what we're talking about for SVM. So remember that's what we have, right? Basically, SVM is trying to maximize this gap, right? As we derived last time, we basically can reformulate the problem as minimizing the weight square with some constraint like this. And yes, Tosa can see that. Okay. So and then we can using Lagrange multiplier to absorb this constraint. Right? If we absorb this constraint like this one, and then we can flip this maximization and minimization and become this. And then if we consider minimizing this one and get some objective function, then maximizing this objective function is known as the dual problem. And this dual and primal problem will be equivalent with this case when the KKT conditions are satisfied. Basically, we have this complementary slackness condition. Basically, this constraint has to be equal to 0 for each of the I, for every I. And also with these constraints here, so alpha I should be bigger than or equal to 0, and this is basically the original constraint, right? And this is basically I'm trying to minimize this guy, therefore the gradient of this part is equal to 0 with respect to W. So these conditions are pretty actually intuitive. Then we show that if the KKT condition is satisfied, that if we try to solve the dual problem, then we have this basically W equal to this, and then we also have, if we take derivative with respect to B, we get this one also. Then eventually we have the dual problem is equal to this. And then we can, this is typical how people solve SVM, but actually it's not what we you see in the homework. Because in the homework they do it in a pretty brute force way. It's not the most optimum way like most people did in here. People typically solve the dual problem instead of the primal problem. But in the homework, just try to tackle the primal problem, then just set the cost there, and then try to minimize using gradient descent. So, but of course, this for small problem is okay. For big problem, probably it's not a good idea. So, but let me let's see. We left off something. I want to talk something of course we mentioned kernel. I will come back to that. Actually, when I look at the kernel, I'm thinking if I can give you another example, then I take it up and I find another example. I like to talk a bit more some more kernel trick. So, but before that, I want to continue because we ended to say how about we have some of this data point that is really kind of get out of the way. For example, this one is not too bad, but maybe we have one of these is here. Then definitely this hard margin SVM, it doesn't work. There's no W that will basically have this constraint satisfied. So then in this case, we need to use a soft margin. Basically, we will allow to have some points that fall inside this gap here. And the cost function we can modify pretty easily. Basically, we'll say if it doesn't fall inside that, we don't have a penalty there. But if it fall inside that, then basically we will have a penalty. As you see, this here, we have an h function here. Is basically just kind of a so-called hinge loss, something like that. So if it's negative, then it's just equal to 0. But if it's positive, then it's just equal to the argument, the input argument. So then this basically if the constraint is not satisfied, then you see this guy will be equal to some positive value, right? Otherwise it would be just equal to 0. So then I can add this penalty also into the, so this is kind of similar to Lagrange multiplier actually. So instead of this hard constraint, we have a hard constraint, hard margin SVM, we have hard constraint here. We introduce a penalty here like this. So any question for this? So
yes. Wanted to know that why is this differentiation necessary after all between hard margin and soft margin SVM? If we can just go with the basic technique, then would it be necessary or enough to suffice our needs?
You mean this one?
Yes. Why do we have to classify SVM into two separate categories of hard margin SVM?
Honestly, I think like most of the time you would like to use the soft margin. We start with the hard margin, just kind of easier to. I'm not sure easier. It's actually a little bit easier. It's actually for the ease of exposition. So in practice, I think probably you can just go for the soft margin basically, to be safe basically, because like you don't know how the data points are distributed, right? That's chance really, you really don't have any solution. But of course this is something tricky, because if you map to the high dimensional space, if you use the kernel trick, then using soft margin may not be as necessary, because if it's in really high dimension, maybe things will get more easily separable. But as a rule of thumb, like let's, I think it's you can always just use soft margin. Yes. So I talk about something that is not useful. It's not, right? It's a kind of exposition that you understand. Yeah. So did I answer your question? Yeah. I'm not sure you're satisfied with the answer. Yeah.
To some extent. Yes, sure. Thanks.
Yeah. So then, okay, but actually like this looks like it has written in the way that it looks like I can just take a gradient or something, but it's not, because I have a mass function here, right? It's not. I can not really. This is actually I'm cheating. If you put it here, if you look at this, it's not something differentiable or like yeah. So instead, like this is another trick here. We can rewrite this problem. So I will introduce a dummy variable here. So I will introduce a C here, a CI here. So basically CI will be like the penalty for each of these guys. So CI will be this. For example, for this red one. And for the others, CI will be equal to 0. So then I will change this into like minimizing 1/2 W square per CI here. Then, but of course, I need to define what is CI. CI should be equal to basically 1 minus this yi w dot x I minus b. So if this thing is positive, right? Otherwise it will be negative. Okay, but of course if you look at that, like I just elaborate that, but it's going to be solvable. So because this CI is like is defined in two different cases. So again, I actually like when I basically I cannot really end here. Like this is not the end of the trick. Basically, what I want to say. So, but I can basically make CI to be, let's see, less than equal to this guy. Oh, let me see if I can erase this. Oh, okay, I can make a constraint that CI is less than equal to this, but also for CI is bigger than equal to 0. See, it makes sense. So I'm using the fact that like for this optimization problem, it's quite clear that like the CI when I have a choice for CI and let's see, I want to make sure I'm correct. Let's see. Yeah, I think I'm correct. Yeah. So let's see, it makes sense actually. I have seen okay, CI is some kind of penalty here. So I want CI to be small, and CI should be small. When wait a sec, it looks something is it looks a little bit weird. Is that when the constraint is not satisfied? Let's see. If I have one of this here, when this is constraint is not satisfied, meaning this is positive, right? This positive is here. I don't know. I thought like I understand that, but this always happen. Like when you start teaching that, you realize it doesn't look like you completely understand. But let me make sure that I'm writing correctly. So this one should be identical to this one, right? Let's see. Here I say bigger than equal to 0. I have y move to this side, right? Oh no. I think I have a sign problem here. Let's see. Yeah, I think I have a sign. Is that this is equal? Okay, let me write it. This is equal to 1 minus ci, right? Y. Well, it looks like it's okay. Oh, okay. If I look at it this way, probably it's easier for me to understand. So this is basically the when I originally want this CI to be equal to 0. Right? When CI is equal to 0, then no, I'm not good actually. CI equal to 0. Let's see. Why I got a bit confused. So anyone can help, or like, do anyone look at this and think, oh yeah, it's obvious, and yeah, I don't know what this guy is like thinking about. Like it's so obvious. Anyone think it's like, let's see. I want to make sure that this is actually solving this problem. Let's see. I have this penalty here. I try to minimize this one. I want CI to be small. This constraint seems that I can pick Ci to be as small as possible, right? Let's see, what was the... Ci should be positive, okay. But this guy is... When constraint is not violated, then this one is I guess I really should look at it, really just start from the beginning. This is the constraint, and when the constraint is not violated, or like when the constraint is violated, let's focus on constraint is violated, then this one is negative, so this one is positive. Okay, this one is positive. I try to minimize this one with Ci here. What made me doesn't choose W such that Ci is equal to 0? Oh, okay, because I cannot, right? This because I cannot, is that? I'm not sure I have written down something wrong in my slides. It looks like, my question here is like, when the constraint is violated, that means that this is positive. What forced me not to still pick Ci equal to 0? I think like it's supposed to be when this is violated, my Ci will be forced to be equal to this guy, but it's not. It doesn't look like it's, yeah. I slip my. Let me make sure I didn't copy something by mistake that.
This is like try to figure out the
Oh, okay, wait. Okay, I see I made a mistake here. I definitely have a mistake in the sign here. It should be this way. So I need Ci to be bigger than that. Yeah, of course, it should be like that. I'm sorry, like I wasted how many time here. Yeah. So, okay. Yeah, sorry about that. Yeah, I didn't have enough sleep last night. So this one here, right? Okay, like this, that is fine. Okay, but I was not way to worry about that because I look at that, it doesn't make sense for what I've written down. So this is like when the constraint is not satisfied. That's, for example, this point here. This is positive, right? So this is positive. We force Ci to be bigger than this guy here. And of course, for this minimization, you basically pick Ci as small as possible. then you want essentially just pick CI equal to this guy. So it's actually equality constraint. And this one will just make sure that CI is bigger than or equal to 0. I don't know what okay. Yeah, sorry, I don't know why I take so much time for this thing. So you guys are happy? Yeah.
What about like these
Mm-hmm.
CI is greater than 1?
CI is greater than 1. But I mean, like, it doesn't matter whether it's greater than okay. I care about this. This is like, this is actually this is actually my penalty here, right? What I want is when there's a penalty, it's actually equal to this guy, basically. You can ignore this actually is equal to this guy when this, yeah. So therefore, basically, there's two cases. When this constraint is satisfied, then I will just pick CI. Then CI can be, this will be negative, right? Then CI just has to be bigger than or equal to 0. Then I can pick CI equal to 0. But when the constraint is not satisfied, then this guy is positive. Then out of these two conditions, I need to pick CI is to be bigger than or equal to this guy. Then of course I am trying to minimize this plus C times CI here. I'll just pick CI equal to this one here. So, okay. I wasted 20 minutes or something. So, really sorry about that. So, this is, so then I will return as this. Then actually you can do the Lagrange multiplier again. Then this is like a standard Lagrange multiplier things, right? This is like, I would really recommend you guys to really know KKTM, like Lagrange multiplier, stuff like that. So at least you know like where, when you need it, you know where to take it up and then use it, because this is so common. So then,
Dr. Chang?
yes?
Is there a method for picking a reasonable C? How do you choose C?
How? This is again a very good question, but no, I don't think that's a very good. This is again like some kind of hyperparameter. It's very typical. Like you have like maybe you have a derailment set or like this validation set that you reserve. So as we mentioned, one of the class, when you have the data, you train the classifier. You always keep 3 pieces. Like you keep a training set, a validation set, and a test set. And for the training set, you can train the model here. Like afterward, you're going to find this alpha I, right? And then you use the validation set to pick your C. So, and after you train the model, you have basically you try different C, and then like for each of the C, you test on your validation set. And you pick the C that gives you the minimum validation error, basically. Did I answer it clearly? Like, so basically you have your data set, you can split into like training, this is a validation, and testing. So you can ignore the testing part. Testing is like after you fix everything, you can use that to compute your error. But you use the training, for example, in this case, you're training, you pick the alphas, right? So you solve your SVM, you find the alphas. But for different C, you have different set of alphas, right? So you can have C1, C2, and so on, right?
So for specific systems, we need to try several Cs to...
Yeah, you basically try to... Yeah, but you cannot test it in the training set, right? Because... so then you can test that in the validation set. So for different C, you have different alpha. Then you test in the validation set and pick the one give you the best kind of performance, the minimum error.
So, but there was so many numbers. How could we,
It's not that bad, honestly. There are many more, like always. Hyperparameter. This is only a single. Yeah. In typical like machine learning, like neural network, there's always lots of hyperparameter. If even you think of like the what model you pick, right? Why you pick so many number of layers? Why you pick Westlet with these layers instead of, I don't know, Google-led or whatever? Then these all choices. You can ask why I picked that. Then it turns out like there's no good way for you to choose other than you just test that in a validation set and just pick the one give you the minimum validation error. Okay, so did I answer your question?
Yes, it did.
Okay, let me. Okay, so for the here again, I guess I won't repeat the Lagrange multiplier, but you see I basically introduced this is the constraint here, right? So introduce multiplier. There's actually like if you're n theta, there's n constraints here, right? So there's n alpha I here, and then I also have this Lagrange multiplier for Ci here. So if you solve that, basically take gradient of L with respect to W, you'll have basically same equation as before. You have W equal to this guy, and if you take gradient with respect to B, you get this one. Again, very similar to previously. And if you take gradient with respect to Ci, you have this one here. Then you substitute this back, you get this one. Again, like quite similar to what we have. Actually, the only difference then is like you actually have a C here, your alpha. That is actually very interesting. Your dual problem is almost identical as before. The only difference is you have a C that David is very interested in. That you basically just your alpha I, actually in this case maybe it's easier than what I just mentioned because you basically have a C just like this. The choice of your C is not, I think it's not as significant as like what it may, I don't know. It depends on when you actually after you solve the alpha idea. So let's see what next. Okay. And as I mentioned, this is the dual problem, and maybe finally I would just say want to kind of give some remark on the different cases, like taking advantage of the complementary slackless conditions. Remember, we have these slackless conditions that like this is equal to 0 and this is equal to 0, right? For every I. So then like this is equal to 0 and this is equal to 0. That will give me, and also I have this one that I mentioned earlier. Then if you look at that, if I set Ri to be between 0 and C, then basically I have alpha I will be like from 0 to C. And then if I use the complementary slackless condition here, alpha I is non-zero, therefore this one is equal to 0. So this one equal to 0. And also because Ri is non-zero, then Ci is equal to 0. So therefore I will have like Yi is equal to that. So that means that like for alpha I between 0 and C is actually is the case for you're hitting this boundary here. It's the classic support vectors that we have in the hard constraint case. And if I have Ri equal to 0 and alpha I equal to C, okay, Ri equal to 0, then from here alpha I equal to C. And then again, because alpha I is non-zero, this guy is equal to 0. So this guy equal to 0, but Ci now can be bigger than equal to 0, right? Because Ri equal to 0, there's no constraint on Ci here. So this can be bigger than equal to 0. What I have is like, I have the constraint can be not satisfied, I think, right? So when the constraint is satisfied, it should be like this. So this is the case when, for this guy here, that violate the margin And the final one, actually, you can go through that also. This is the case that is outside. So basically, when alpha I is equal to 0, that will be like the case. Again, like it's similar to the hard margin case, if you remember. When for everything does not violate the condition, that's basically in the hard margin case is not the support factor, then those alpha I will be equal to 0. And if you remember, like W is basically equal to this alpha I. Actually, I have that here, right? No, do I have it here? No, I don't. W is equal to this way. W is equal to alpha I times Yx. Actually, of course, I should look at the soft margin, but I think it's the same. Yeah, W equal to alpha I times Y. So therefore, like similar to the hard margin, like if it's not violating the constraint, those parameters we don't care. Actually, it won't affect the final result. Only those hitting the boundary, hitting the margin, or like violate the margin, will have alpha I non-zero. So any questions? And finally, I guess I just give a very quick for multicast. This one, I won't go into detail, but you can do it as an exercise. It's similar to in what we have for generalization from logistic regression to softmax, something like it. So you can, if you have more than one classes, then what you have is that you can have like different scores that is generated by like different weights multiplied by your input, and then you will just try to pick the score that is highest will be your estimated class, and also you want that your score that is that hopefully the score if you have a class, maybe let's say I have a cat, dog, and pig, something like that. I have 3 classes, and if that ground truth is a cat, then I hope the cat classes, the score of the cat classes is higher than both dog and pig by some margin, let's say some margin delta here. And here I can do something like in the soft margin SVM. So if that margin is less, if it's violated, so it basically, if it's bigger than this margin delta, then it's fine, that the loss will be 0. Otherwise, my loss will be basically that whatever the difference can be. And then I can add this loss into my cost function. So basically, for each of the sample, I look at each of the possible classes and see, like, for each of the classes whether the cost is if it's like the ground truth cost, ground truth score is bigger than all the rest plus some margin. If it is, then the cost for those will be 0. Otherwise, that will have a positive cost. I will add all those together and add that to my whatever this W square that we have in SVM earlier, then just solve this whole problem. So, okay, this is a very quick, but I think it's like more or less very much similar to the other cases. So I think you can use by now you should be able to derive or pick it up like in literature or something if needed. And now back to the kernel. Maybe I re-emphasize the kernel part. So let's see, where should I use? Maybe I use somewhere here, right? So I maybe here look at the primal problem again. So look at the primal problem. So assume that now if I want to use the kernel trick, so basically I can project my input, and also the weight, to some high dimension. So I will have W project to find W. This is a much higher dimension, and X project to find X. Right? So here I can think of like this original primal problem will change to this is I find W, and I have find W dot find X here. But the trick here is that I don't actually compute this projection. I mean I don't actually even need to recompute anything. I mean I would just assume, okay, I'm going to do this, but instead of maximizing W, now minimizing W, I'm minimizing find W, right? So find W is now a much longer vector. Maybe the original dimension here, W is a D, maybe this is a, I don't know what words I didn't use, maybe K, big K here. So I just will basically minimizing, instead of like W, small W have only D scalar variables, I have like big K so many variables. Here I don't know, it doesn't need to change anything, so therefore like the dual problem doesn't change also, right? So the only difference now will be like this, the solution will be like find xi dot find xj, right? But the nice thing is that like we only need to know the inner product, right? So therefore like we actually doesn't need to compute this guy. Instead we can introduce a kernel function. Basically a kernel function is a when I say kernel xy is equal to the inner product of like find x and find y. So that means that I don't actually know what is find x, and I don't know what is find y, but I just know like what is kernel xy. And an example like we mentioned last time, it can be a Gaussian kernel, like I can have like kxy is e x minus y square over sigma square, for example, right? Can be a Gaussian kernel. Then you just have this kxy replace this guy, right? Kxi xj, basically replace this place here. Then you can just solve for alpha I of j as before. And after you solve that, then when you actually use that, you need to have like W, what is it? You need to, when we use that, we need to compute what? W dot x, right? Something like that, right? You need to compute this, right? Sorry, Wx. Let's say this is new x here. So then W multiply x will be just this guy dot new x, right? Again, like here, I don't actually need to know. Sorry, I'm sorry. This is like find W and find x, right? We need to compute the inner product of the in the projected space. And again, I don't need to know like what is find xi and find x. Here will be just the kernel function, right? It will be kernel xi and x, something like that. This W find x, find W find x, something like that. Oh yeah. So any questions?
Just as part of the multi-class SVM, I was interested in understanding how does the graphical visualization works when we are using a multi-class SVM as a classifier. Where do the line go, and how can a single line be used to basically classify more than two classes?
Actually, for multi-class SVM, it won't be single line. If you look at that, like it would be more or less like something like this. 3 classes here. You are basically trying to okay. I don't know, it's a little bit hard to visualize, but it'll be something like this. You look at, so you think of the score is basically as projection, right? For example, I have 3 classes here. I can have, for this class, I can have a score basically along this direction. Something like, or maybe this direction. More into here, it will have a larger score. So for example, here I have a score like for this, maybe this is cat class, dog class, or pig class here. So then like maybe this is like for the cat score is 0, cat score 1, cat score 2 here, right? This is a cat score 3 here. So anything like along here, for example, all this will be cat class equal to 2. For example, this one will be cat class 2 as well, right? Is that clear? So now similarly, I can have dog class here. My dog class score will most likely look like this. And along this, maybe this is my dog class equal to 0, dog class equal to 1, dog class equal to 2 and 3 and so forth. So then my my selection of the actual value, it may not be too nice. Maybe I set instead like 0, 1, 2, let's see. Maybe this is a 3, 4, 5, let's say, right? So therefore, a point here, if you look at that here, the point here, for the dog class, the score will be like at least 3.5, right? This is a dog score for this point here. But the cat score here is equal to, actually is equal to minus, actually my original values is okay, minus 0.5, I don't know whether it makes sense to you. Does it make sense to you? Like this maybe around minus 0.5. Okay. So if I just look at dog and cat class, then it will pick the dog class, right? And I can also have the pig score, most likely, maybe I use another color. A pig score will be along this line, right? Something like along this line. And then like around here, maybe pig score is like 1, and then this is pig score 2, and so on. Okay. So again, like this one is like the pig score probably is pretty low as well. And what you want is like, you have any point here, any training point here, if it's a dog class, you better have the dog score is larger than the rest of the classes, right, by some margin, delta. Maybe I can pick delta is equal to 1, for example. Then I will want to, if dog score is 3.5, I will hope that like for the same point there, the cat score and the pig score is at most like 2.5. Is that clear?
Yeah, to a certain extent.
Yeah, so the boundary is hard to draw like here, as you can see. Like, yeah, probably will need to have some visualization tools, but yeah, it'll be yeah, but it's still drawable. Most likely, it'll be something like this, that kind of like boundary. Yeah. So okay, I have 20 minutes. 30 minutes, 20 minutes, something. So okay, I since I prepared for that, I really want to. Okay, I have this one example here is, as I mentioned, using the kernel trick, right? So let me give you one more example during kernel trick. So let me maybe I create another scenario. So consider the kernel PCA. I think Robbie mentioned PCA before actually somehow. So you guys all know PCA, principal component analysis. So it basically you just have some data in some high dimension, then you kind of like want to see like what is the which components along which direction it has highest variation basically, right? And that's the original PCA. And for example, like this along this direction, it looks like those data points have highest variation. So then this is my first principal component and first principal component. So if I want to, for example, reduce the dimension of the data, maybe original data is like big D dimension, maybe D is equal to 10. Maybe I can just reduce to 3-4 dimension and will be sufficient to represent the data. I will just go along the axis that have like the highest variance. And the highest variance, if you remember like how we get that, or like if you don't know, basically like this principal component, you get this by decomposing the covariance matrix, right? For example, I have data points like x1 up to xm, and each of them have dimension d. Then I can estimate its covariance matrix. Maybe C is equal to xi, let's see, this all of them are column vector here. xi transpose 1 over n. Assuming all this data point is already zero mean, so I assuming they are zero mean. Then if I decompose this like with argument value decomposition, namely if I have like CV is equal to lambda v, let's say, or like CV I equal lambda IVI, then I can sort the eigenvalue. Then the first VI, the eigenvectors with the highest eigenvalue will be the principal component, like this one, the first principal component. And then the next eigenvector with the second highest eigenvalue will be the second principal component, and so on. So this is PCA. Any question for that? So I think many of you should know that already. So but if not, okay. Any question? Quick question, like so. That basically you okay. The objective of PCA is you want to reduce the dimension typically. So you have very high dimensional data, and for example 100 dimensions. Maybe afterward you want to pack into a classifier or a simple classifier. You for some reason you don't want to have so high dimension, or like you want to visualize that, right? If you visualize that, I can only look at just 2 dimensions, right? So then I want to pick the dimensions is have highest variation. So in a very high dimensional space, for example, like here I draw it like assuming this is not 2D, at least a 3D or 4D data. I want to draw along the axis they actually have variation, right? So I want to find the axis they actually have variation. So how to find that is pretty easy to show. That is basically this component, the highest variation, just correspond to the eigenvector of that covariance matrix. Yeah. You can think of a special case if you need some intuition. For example, if you have a special case, everything is each of the dimension basically independent, then you will have the principal components will be just orthogonal to all the axes, and then basically the eigenvalue in this case will be the variance at each of the axes, right? So what we are doing is basically just we pick the axes have the highest variance that correspond to highest eigenvalue. Yeah. So now kernel PCA has some are the rationale behind that. So what we're trying to do is like, again, like for classical PCA, you have data points like similar to like we extend from SVM to kernel SVM. You may have data points that basically not separable. Like for example, I have data point like this. Then PCA is not very useful. So I try to. There's a goal that like I basically you can think of this. This is like similar to kernel SVM. You can apply this similar to a kernel SVM, but you don't know the label. You don't have the label. So you don't have the label, but you still want to somehow make it separable. So you have maybe you have points like this, and then points like this. You want to have some kind of unsupervised learning, and you want to separate into classes. So in this case, one possibility, of course, is I use the kernel trick to project to higher dimensions, right? Project to higher dimension, then there's possibility that you can separate them. And if just for the sake of separation, then I don't really need to project to really high dimension. Actually, I can project to just the number of data points, because if I have n data point, I project to n dimensions. Basically, if you think of you have n dimensional, for example, 3 dimension, 3 data points, it's almost you can separate them, right? So also if you have n dimensional data, n data point, you project to n dimension is typically sufficient. So that's basically the introduction, the background behind that. So I have some handwritten notes. Hopefully I don't get stuck in the middle like I did previously. So classic PCA, you're trying to estimate the coherence matrix like this, right? Now I will do the same thing. I assume like data is already zoomed in. So and I projected that to find xi and find xi, right? So in high dimension I have a coherence matrix like that, right? Something like this. Now the main trick here, there's like several trick here. The main trick here is like we realize that actually this will be an eigenvalue, eigenvector for this coherence matrix. I can say V alpha I find xi. So it turns out like for any choice of alpha I here, this will be an eigenvector for this coherence matrix, for this matrix here. So it's quite easy to show. Right? Let me just quickly go through that. I will see V here. So it's I1 to n, 1 over n, find xi transpose. So I better use a different dummy variable here. I use j here, find j equal to 1 to n alpha j, find xj. So let's see. If I multiply that, so then let's see. Then what you can see is what can I do? Oh, actually, I want to do another way. I'm sorry about that. So I make a proof here. So let's assume that I have V is the eigenvector of this guy. So I have this multiplied by. So basically, this matrix multiplied by some vector V is equal to lambda V. Okay, that's because V is eigenvector of C, therefore I have this. Now then, that's the simple thing. So you see this is actually a 1 by n vector, right? This is basically just an n by 1 vector, right? This is actually a scalar, so I can just write here. Actually, this is just a dot product. Find xi. So then you see that like this is basically just a scalar, right? So this is essentially my alpha I. See? So for any vector that is an eigenvector of C, it turns out can be just written in this form, right? So therefore, it's just this guy here. So it's just some alpha I and 10, kind of like it's just weighted sum of pi xi, basically. Now let's see. Now let's since my V can be written like this way, let me substitute this back to here and see what happens. So if I take a V as this form, I want to see like if I can solve out alpha somehow. So let me substitute this. Maybe I just erase something. It's better than moving back up and down. So I just substitute into here. So then I have 1 over n equal to 1 to n phi xi transpose V, let me use j here, alpha j phi xj is equal to lambda, is this again, j to 1 and alpha j phi xj, let's say. Oh, let's see. It look a little bit ugly, but actually it's not that bad. So my intention is I want to create a kernel matrix. So remember, what is that kernel matrix? The kernel matrix is should have the ij element is equal to phi xi phi xj phi xi transpose phi xj. So note that that's different in transpose here. This is the C matrix, is this. But for the kernel matrix, the ij element should be just the inner product of the I phi vector with the j phi vector. So I think I can make it like this. So I already see this thing is pretty much is equal to k ij, right? So it looks like if I multiply phi xk transpose on both sides, on both from the left, then I will have like this multiplied by this, I will equal to k I, right? And this I have k I j. I have alpha j somewhere, alpha j. So I can have some over j, maybe some over j, put it here, some over j, some over I is equal to this. I get k j alpha j, right? So then for this one, I can move this summation around. I can move summation j equal to 1 move to the front, and then as I put alpha j here, and then have I equal to 1 to n, this k I j here. So you see that this is what? This is actually just k square k kj element, right? The kj element of the k-square matrix. And this is actually just equal to k alpha, the k element of k alpha, right? So this also I can combine that. This basically is just k square alpha, the kth element of k square alpha, like that. So therefore, like, it just means that k square alpha 1 over n equal to lambda k alpha, or you have like k alpha equal to lambda alpha. So that's super nice. Actually, that means that alpha is actually has to be the alpha. Remember what is alpha? Alpha is like we say that the eigenvectors, the kernel kernel PCA, the kernel principal component can be linearly decomposed into alpha, weighted sum of like finite xi with alpha, right, with weights alpha, right? So, but we need to know what's alpha, right? But it turns out alpha is actually just eigenvector of the kernel matrix K. So then that more or less it. Then basically then we can solve alpha, right? Because like this will be just eigen decomposition of K, and then like similar to like PCA, we basically pick alpha such that we start from the corresponding eigenvectors, corresponding eigenvector with the higher eigenvalue. And I guess I just give one final remark here is, if you look at here at the beginning, we are assuming that like things are zero mean, right? Because we are assuming phi xi is zero mean, but it's kind of difficult to make it zero mean because, I mean, like it's basically impossible to assume zero mean to begin with. But luckily, what we can do is like know that because K basically what K matrix is like just is I can write it like phi x1 transpose phi transpose x and phi x1 phi xn. This is my K matrix. So in general, like if I want to make this thing zero mean, so I can introduce a centering matrix. Basically, like think of like if I define Cn equal to I minus this In minus 1 over n I 1n. This 1n is basically like all one matrix here. Then Kcn, what's Kcn? Basically it's just equal to K minus, okay, if you think of like K here, it's like n column vectors here. Then what we have is essentially like, let's see. This multiplied by this guy here will be just getting the average of the column vectors here. So therefore, like Kcn or K multiplied by In minus K multiplied by 1n over n will be just kind of averaging K along the, averaging over all the columns. And similarly, I have Cnk will be like averaging over all the rows. So therefore, like if I apply this, basically with will force like the matrix to be zero mean. So, yeah. basically. Then, or like you can elaborate that, and therefore like you can, instead of like working with k, you start with a k, but you work actually with k tilde is equal to Cn times k times Cn, something like that. So I guess I'll just show you one quick slide, then we'll stop here. So sorry, like the last couple of minutes pretty quick. I wasted too much time at the beginning. So this is an example. So this is a summary of like kernel PCA. So therefore, so you start with like compute the kernel matrix. The kernel matrix is like the ij element will be the inner product of your or not actually inner product. It's basically kernel. The ij element will be just equal to it's the inner product of your projected value. But let's see if I can. Why I cannot? Okay, now I can. Where's my sudo? So what I mean is say that is equal to ij element of that, right? But the inner product of this is just equal to kernel function, right? So essentially, of course, you don't need to care about the find, but you just compute the find x1, find x1. Basically, k is just kx1, x1, kx1, x2, and blah blah so on. So you have this kernel matrix there. And then I compute the kernel matrix. Then you try to make it half zero mean. So as I mentioned, like at the end very quickly, you can make a zero mean using this. Just and then like you solve the eigenvalue for k. Then the eigenvectors will get to alpha. So then your data point will be the eigenvector, then eventually the eigenvectors will be this way. This will be the eventual eigenvector. So that means that you can project into those directions. So this will give, let me just show you that some example. Like this is the input point, that the original points. If you do the kernel PCA and look at the pincer component for the different pincer components, you get the points I get kind of separated nicely, and you can use that for denoising. For example, this is you use for denoising is like this. Have like some data with some Gaussian noise. Then this is just using linear PCA. So basically, you denoise by for how do you denoise in classic PCA? I guess I'm watching it. I guess I'll come back and like go back a little bit. I guess near the end is watching it too much. So Tosa, are you guys okay? Oh, I'm not sure you guys are still here.
I'm good in Tulsa.
Okay. So okay. Yeah.
When you say denoise, are you just talking about after you eliminate after you go to lower dimensions, then you're reconstructing it back to the higher dimensions with those?
Yes, but then you set some of this component equal to zero, right?
Yeah.
Yeah, that's
how
one.
eigenfaces are done.
Yes, you remove some of this. Yeah. Base for some bases, you just keep the component that has highest variation, basically. For the rest, you just discarded that. And kernel PCA will be similar, actually. But maybe like I'll just give a very quick review next time. I mean, kind of summary next time, because I guess I feel like I'm really watching it near the end. So okay, so I see you guys next week. Today or tomorrow, yeah.